Let's be a non-real complex number satisfying z to the power of 23 equals 1. We want to compute s, the sum from k equals 0 to 22 of 1 over 1 plus z to the power of k plus z to the power of 2k. The key tools will be a permutation of the exponents and a geometric series. Since z satisfies z to the power of 23 equals 1 and z is not equal to 1, z is a primitive 23rd root of unity. This means 1 z squared all the way up to z to the power of 22 is exactly the complete collection of all 23rd roots of unity. We will use this completeness crucially in a later step. Let's pull out the k equals 0 term first. Every z to the power of 0 is 1, so the term equals 1 over 3. The sum then splits into 1/3 plus the remaining 22 terms. For k between 1 and 22, z to the power of k is never 1, so all the denominators in the remaining sum are non-zero and well-defined. For any u different from 1, we have 1 plus u squared equals u cubed minus 1 over u minus 1. Taking u equals z to the power of k, we can flip this identity. 1 over 1 plus z to the power of k plus z to the power of 2k equals z to the power of k minus 1 divided by z to the power of 3k minus 1. Substituting into the sum gives this rewritten form. Here is the crucial step. Since the greatest common divisor of 3 and 23 is 1, multiplying by 3 is a bijection on the non-zero residues modulo 23. Set m congruent to 3k mod 23. The inverse of 3 modulo 23 is 8, because 3 times 8 is 24, which is congruent to 1. As k runs from 1 to 22, so does m. Substituting k equals 8m gives the rewritten sum on the right. Now we use the geometric series identity. Z to the power of 8m minus 1 over z to the power of m minus 1 equals 1 plus z to the power of m plus z to the power of 2m all the way up to z to the power of 7m. Summing over m from 1 to 22 and swapping the order of summation, we get the sum over I from 0 to 7 of the inner sum of z to the power of im. For I equals 0, the inner sum is just 22. For each I from 1 through 7, all 23rd roots of unity sum to 0, so the sum from m equals 1 to 22 of z to the power of im equals -1. The total is therefore 22 plus 7 times -1, which is 15. Putting it all together, s equals 1/3 plus 15, which is 1 plus 45 over 3, giving the final answer 46 over 3. The key insight was that the coprimality of 3 and 23 allowed a clean index permutation, and the resulting geometric sum reduced to a simple count of roots of unity. Before we finish, here is a challenge for you. This time let w be a non-real complex number satisfying w to the 11th equals 1. Can you compute the analogous sum from k equals 0 to 10? The same method works. Check whether 3 and 11 are coprime and follow the same steps. Drop your answer in the comments. Coprimality, a clean index substitution, and the vanishing sum of roots of unity are all you need to evaluate this elegant expression. Thanks for watching. Like, share, and follow Hamifi's Visual Maths. See you in the next one.